Welcome to Chemistry Revision on the Move. Kinetics. So let's consider a generalized chemical reaction where we've got X moles of A and Y moles of B reacting together to form our products. Now, the rate of this reaction may be dependent upon the concentrations of A and the concentration of B, but we can't just look at that chemical equation and state that that is so. All that we can do is write a generalized expression where we say the rate of the reaction is going to be equal to or proportional to the concentration of A in some way, let's say to the power n, and B in some way, let's say to the power m. Now, under those conditions, n and m could potentially have any value possible. They could, for example, n could be 1, m could be 2. They could have fractional values as well. So all that we can do is we can say that those values are there. If we want to determine it, we need to look at an actual experiment. Just by looking at the equation itself, we cannot determine those values of those n and m values. Now, what we have is those two values, n and m, are given names as orders of reaction. So if n equals 1, we would say that the rate of reaction is first order with respect to A. If m were equal to 2, then it would be second order with respect to B. It could possibly be 0 as well. But if we were to say n was equal to 1 and m was equal to 2, the overall order, which is the sum of the orders, is going to be equal to 3. So n equals 1, first order with respect to A, m equals 2, second order with respect to B, third order overall. Now, if we have our rate expression there, not only do we have the values of rate and concentration of A and B, we also have our rate constant K, lowercase k, as you can see in the middle of the equation. There it is. And once again, this needs to be determined by experiment, or at least its value needs to be determined by experiment. So if we take our equation, once again, rate equals K, concentration of A to the power n, concentration of B to the power n, and rearrange it, we will get rate over concentration of A to the power n and concentration of B to the power m. Now we can determine the units of K if we know the orders of reaction n and m, because our rate will always have units moles per cubic decimeter per second. Remember, it's change in concentration per unit time. And concentration of A, of course, is going to be moles per cubic decimeter, but we will have moles per cubic decimeter to the power n for the concentration of A, and moles per cubic decimeter to the power m for the concentration of B. So, the units of K are going to be, as you can see, dependent upon the overall order of reaction. So if we take a situation where the overall order is 0 order, in other words, n and m in this particular case would be equal to 0, what we are saying is that the rate of reaction is independent of the concentrations of the reactants. So our equation would reduce to rate equals K, and under those circumstances, the value or the units of K would be equal to moles per cubic decimeter per second. If we take a first order reaction. In that particular case, overall order is 1, so therefore it's going to be rate over concentration of a reactant to the power 1. Units would be seconds to the minus 1. Second order, following in the same way, rate moles per cubic decimeter per second divided by concentration moles per cubic decimeter all squared. The units come out to be moles to the minus 1 decimeters cubed seconds to the minus 1. And third order, following the same pattern, moles squared decimeters to the 6 seconds to the minus 1. So therefore, by considering the units of K, you can determine the overall order, or looking at it the other way, by knowing the overall order of reaction, you can determine the units of K. Now, if you cast your minds back to the Maxwell-Boltzmann distribution curve, you will remember when you change the temperature of a reaction, the distribution of energy of the particles will change as well. And you find that many more particles have energy greater than the activation energy, and therefore as you increase in temperature, the rate of reaction will increase exponentially with increasing temperature. So you will get a graph that looks a little bit like that. Now, how can we relate this to the rate constant? Well, we know that the rate constant K is a constant at constant temperature. But if you think about the rate expression, as you increase temperature, whilst the rate increases, the concentrations of the reactants don't increase. Therefore, the factor that increases with an increase in rate must be the rate constant. So therefore, what we can do is we can say our rate is proportional to K, and therefore we can, when we change temperature, say that our rate constant K increases exponentially with increasing temperature.